Good morning, friends. My name is Ashutosh Garg. I work as a solution provider with Furnace Improvements. Our company is in the business of revamping fired heaters. We can revamp your cooker heaters to the longest run length, highest efficiency, highest capacity. This webinar today is born out of my experience of dealing with customers for more than 40 years. This is our fifth webinar, and I welcome you all. As you are all aware, the whole world is experiencing COVID pandemic these days. I hope all of you are keeping safe and following all necessary precautions. There is some light at the end of the tunnel. We are going to have COVID vaccine available very soon. And hopefully in the next 6 to 9 months, we will get back to our business as usual. We'll be talking about how to maximize cooker heaters efficiency today. Sorry. Learning is a continuous process. We have learned so much in the past month while preparing for this webinar. Please don't hesitate to ask me a question at any time. Please feel free to share your experience with us. We are going to conduct this webinar through a PowerPoint presentation. We will have the presentation for about 50 minutes, and then we will have question and answer session for the last 10 minutes. We have been able to improve our webinars based on your feedback. So I request all of you to complete the survey before you leave and send it to us. I will start the session with a brief introduction of myself. I'm a chemical engineer. I passed out from IIT Kanpur in 1974. Since 1976, I've been working on fired heaters and combustion systems. I have worked in KT India, Engineers India, and KTI Corporation in the US. Since March 1996, I've been working at Furnace Improvements, fixing heaters for the past 25 years. I want to take this opportunity to mention two periods in my career that changed my thinking. I worked as a startup engineer for almost 5 years with KT India. During that time, we used to face so many problems in the plant, and I would spend months at the site fixing them and getting these plants and fired heaters to run continuously. Similarly, in 1990, when I first moved to the USA, I was given all the heater problems that the company was facing. First-hand exposure to these problems was very useful. I did not visit a single site, but I was able to fix all these problems from the office. So when I started Furnace Improvements, I decided to put our clients first in all our working. I made a commitment to myself that we will provide the best services, the best equipment to our clients. That's our philosophy, and it has worked very well for the past 24 years. I want to start out by thanking our team in the US and in New Delhi for working hard for the past 4 weeks. Our team of process, mechanical engineers, designers have been working on this presentation, putting it together. I am just the deliverer or the front face for making this presentation happen. I want to make sure that everybody can log into the webinar correctly. You will see a control panel on your screen. You should be able to select the sound, the audio input either through phone or your computer. And there is a question box at the bottom. You should be able to type your question in the box and send it to us. I will answer all the questions in the end. There is an orange arrow on the top, and you can minimize the control panel on your screen by hitting the top red arrow. We will make the webinar recording available to you in case you are not able to sit through this session completely or you miss any part of the presentation. If you're not able to hear clearly or have a display issues, please send us a message and my colleagues will be able to take care of the problem. I want to start with a brief introduction of our company, Furnace Improvements. We started in 1996. We will be completing 25 years in the big business next year in March. We currently have 3 offices. The head office is in Sugar Land, Texas. We have an engineering office in Noida. We started it in 2005. And we have almost 35 people in that office. We are doing everything in that office: process, mechanical, structural, design, drawings, drafting, everything is being done there. We are a full service heater company and we can execute projects on a turnkey basis, including erection. Our CFD office is in Pune, India. It started in 2014. Our CFD team has been working exclusively on combustion, heat transfer, and fluid flow problems. Most of our business has been working on improving the performance of existing fired heaters. We try to breathe new life in these furnaces. Each coker heater is custom and unique. The problems being faced by the clients are also different in many cases. We study each heater and carry out root cause analysis in a very systematic way. We have also challenged conventional approaches being followed in the design of the heater. We have some new technologies that can help you optimize the operation and maximize the run length of coker heater. I will talk about one such inclined firing technology today. So that's basically a little bit introduction about our company. This morning or this evening, to all my listeners or participants from India, we are going to talk about coker heaters and the run length. We will talk about different configurations of coker heaters, talk about advantages, disadvantages. Then we'll move to the critical design parameters that you need to pay attention when you're dealing with coker heaters. We'll talk about 2 coker heater case studies where we helped client improve the run length of their heaters. And then we will have the question and answers in the end for about 10 minutes. So let's talk about coker heaters. And today we will be talking about the heaters which are there in the refinery. Typically, a refinery has a number of units and they convert crude to gasoline, diesel, and other useful products. The number of heaters in any refinery could be anywhere between 15 to 60. But the 4 important heaters I have listed over here are atmospheric heater, where we heat the crude to about 700 degrees. Then comes a vacuum heater, where we heat the feed to 800 degrees and subject it to vacuum distillation. And the residue from atmospheric, vacuum, and all other units is collected and sent to the coker heater. In coker heater, the feed is heated to almost like 930 degrees F or 500 degrees centigrade. Here, these bottoms are converted into useful products and coke. It has acquired extra importance in refineries all over the world as refineries have stopped firing liquid fuels in their heaters and boilers due to pollution. That leaves refiners with no choice but to install a coker unit. The coke produced is burnt in power plants and used in many other industries. So these four heaters are very critical heaters. The last heater we want to talk about is the reformer heater, catalytic reformer unit. And here we heat the feed to almost like 1000 degrees F. But the difference is it's a very light feed. It is naphtha and recycled gas. And the heating is done in the gas phase. So it's a very different heater. So, but our attention today or our focus today will be on coker heater. So in coking unit, our objective is to process this heavy material, vacuum residue and all other residues to higher value products such as gasoline, diesel, LPG, and petroleum coke. So what we are going to do is to heat the charge rapidly in the furnace. And this is a very uh, critical furnace uh, because there is a reaction taking place. I mean, if you look at all the refinery heaters, there is a simple heating or heating with phase change taking place. Here, it's not only heating and phase change, there is a reaction taking place, and about 6% of the feed is cracking per pass. And it is an endothermic reaction, and the heater is supplying the heat. So in this heater, we expect coking to start from day one because the feed is such and we are cracking, so the coke starts depositing. And two things happen. Pressure drop goes up and the tube metal temperature also starts going up because coke is an insulator of heat. Lot of people, they inject boiler feed water or steam to minimize the cracking. And it's basically the rate of coke deposition which determines the coker heater run length. So run length is a very, very important parameter, and we'll come to that in a few minutes. So coker heaters, there are two types of coker heaters currently in the refinery. The single-fired coker heater has been the classic heater, and the double-fired heater is the modern heater. In single-fired heater, as you can see from this sketch over here, you can see there are two cells, and in each cell we have a central bridge wall, and we have tubes on the wall and burners in the center firing along or at the bridge wall. So what the function of bridge wall is to divide the radiant cell into independently controlled cells so that you can monitor and control the outlet temperature of each pass. So that is the construction of the classic heater or the single fired heater. We do put the last 5 tubes, if you see over here, at 3D pitch. The last 5 tubes have been put at 3D pitch typically, and that is done to minimize the radiant heat flux in the hottest section. The convection section has process coils and steam generation coil, and then on top we have the stack. So this is the construction of the single-fired coker heater. The double-fired coker heaters were introduced in 1980s. So typically in 1980s, and this became very popular. The advantage in double-fired heater is because we are firing from both the sides, as you can see over here in this sketch, we have the tubes in the center now and burners on both the sides. So because of this, we are able to use higher flux, and keeping the same maximum flux, we are able to use almost 50% higher flux. So if in the single fired, I'm using 10,000, in double fired, I can use 15,000. So when I do that, I can shorten the length of my coil because I don't need that much surface area. And as a result, I have two choices. I can keep the same velocity and have lower pressure drop, or I can increase the velocity, fluid mass velocity, and maintain the same pressure drop. It does offer lower residence time, lower coking, and more uniform heating of tubes. So this is some of the features. As you can see over here, typically each pass is almost like a cell over here. So one pass is like cell. And here also the last 5 tubes are put at 3D diameter, and the convection section is on the top in the center. There is one extra feature which has been incorporated in double fired heaters, and that is because each pass has its own radiant cell or radiant section. The designers are able to offer online spalling. So online spalling, what you do is you cut off your feed and inject steam. And when you inject steam, it kind of breaks the carbon coke from the tubes and removes the coke. And we can do that. And once we do that, it will lower the tube metal temperature. So let's say it is a 2-pass heater or 4-pass heater. We go on a reduced load, inject steam in one pass, and then clean it up partially, and then go to the second pass. And if there is a third pass or fourth pass, we do that. So that is one advantage which is there in double fired, and refiners make use of this facility to spall their heaters, reduce the tube metal temperature by about 100 degrees each time. But after 2 or 3 spalls, they again have to force or clean their fired heaters or coker heaters using pigging. Uh, so the question comes over here, if this heater is so good, what went wrong? Because in the last 5 years, there were 3 or 4 clients who have modern double-fired coker heaters, and they were experiencing only 3 to 4 months run length. So we started studying all the heaters, coker heaters, which we have worked on in the past 25 years. And we made a survey and we found several deficiencies in the double-fired coker heater design. And these things happen when everybody starts building coker heaters. Everybody, all heater companies can offer coker heaters now. And when all companies can offer the coker heaters, it becomes competitive. And once it becomes competitive, vendors start cutting corners and start trying to make heaters more and more compact. And once they do that, you have short run lengths. So if you cut corners, you will get nothing but short run lengths. So but that's what we want to talk about today, is how can we improve the run length. But the reason I'm saying is this has been a problem. We thought double fired heaters will be able to offer 1 year run length or even more, but I think the heaters which we are seeing in the industry are not able to do that. There is a couple of things like in coker heaters, tubes generally last for about 10 years, 8 to 10 years. So every 10 years, you can upgrade your coker heater while retubing the radiant section or retubing the convection section. So you do get a chance to make it right, or at least partially right. And same thing you can do with the burners actually, that if you feel that burners are the ones which are causing problems, you can upgrade them or change them. It is not very expensive. So let us see how coker heaters are designed. So generally, the designers or the licensors will give you a few guidelines. And sometimes they give you the coil design or the box design, but most of the time they tell you, okay, let us keep the cold oil velocity greater than 6 feet per second. Let us keep the mass velocity around 350 to 400. Keep the flux less than 10,000 for single fired or 13,500 for double fired. And inject boiler feed water or steam, which could be around 1% of the heater feed. So these are some of the guidelines, rough guidelines given by the uh, licensors, you can call it, or the people who are building coker units, So that's typically what we get. So we did a database of almost 38 coker heaters we had worked or studied in different times. And most of the coker heaters are multiple radiant cell horizontal tube box heaters. The flow is from top to bottom. Average inlet temperature is around 600 degrees, outlet is around 930. Inlet pressure about 361, outlet around 70 psig. So it's about 290 pressure drop is the average pressure drop across this heater. Average mass velocity around 400 pounds per second plus foot square. Typical flue gas temperature approach from process coil is around 200 degrees. So, I will tell you a little later the importance of this approach, but to me, it appears very high. And other thing which we noticed was the firebox height to width ratio. Surprisingly, single fired had lower height to width ratio of 1.5 or 1.75, and the double fired were offering 2.02. And some of these heaters have even height to width ratio of 4, because if you put 2 rows of tubes in one firebox, you're basically cutting the width into half. So they even go almost 4 times. So this is the typical analysis of coker heaters we want to talk about. Uh, what are the different parameters, when we design these things? As I said, fluid mass velocity figures into the coil side parameters, average heat transfer rate, coil size, and pressure drop. These are some of the four. When if you're designing a coker heater, it will be given to you. And these are all important parameters. Let us start looking at these. Fluid mass velocity is a very important parameter. It is mass flow divided by the flow area of the coils. The units are pounds per second plus foot square. As we said, average is 409. Now, one thing you have to realize is pressure drop is proportional to the square of mass velocity. So if you increase the mass velocity, the pressure drop will go up. Another thing you have to also see is the inside heat transfer coefficient. And inside heat transfer coefficient is important because it controls the film temperature, and film temperature controls the coking. So inside heat transfer coefficient is proportional to the mass velocity raised to the power 0.8. So you can go for a higher pressure drop, higher mass velocity, and it will give you the low film temperature or higher run length, optimized your run length. The flux, this is the database. The range for single fired started around 8,000 to 13,000, double fired 10,000 to 15,000. And you can see maximum fluxes in double fired are much lower as compared to the single fired. So the third thing before I go to the coking rates, I want to talk about the tube size. And typically in coker heaters, the smaller the tube size, the better off you will be actually. Although you don't want to go lower than 3-inch, because if you have to clean it or remove coke, you will have trouble. So 3 inches typically the lowest size, but 3.5, or 4 inches typically the sizes which are used in coker heater designs, and they offer the best surface to volume ratio. You want to have the highest surface to volume ratio so that you can heat the coker feed uniformly. So let's look at the relative coking rates, and this is a chart from Nelson, which he did it in almost like 70 years ago. And you can see there are 3 parameters plotted over here. There is a fluid mass velocity, relative coking rate, and rate of heat absorption. So you can compare that. Lower the flux, the lower will be the relative coking rate. Higher the mass velocity, the lower will be the relative coking rate. So you can see the importance over here, and how you can optimize your coker heater design or coker heater operation by trying to see if you can optimize or maximize the fluid mass velocity. So let's talk about the fireside parameters. And fireside parameters are heat release per burner, burner to tube distance, burner to burner distance, and burner to air side pressure drop. And these are very important parameters. They determine how long your flame is going to be, how high your flame is going to be, how is the heat distribution in the furnace, how uniform it will be, So these are very important parameters. And the reason I'm talking about these parameters is that these parameters do not affect the design of the coker heater. When you're designing the coker heater, or when you're designing any heater, these parameters do not play any part in the design, and it is left to the designer experience to take care of these. And this is where most of the coker heaters fail, actually. And I will show it to you how people work and do it. I think all of you know, fired heaters are designed using correlations designed by Lobo and Evans back in 1940s. And they assumed that there is going to be uniform heat transfer in the firebox, or it's going to be continuously stirred tank reactor model. That is a basic assumption. Now, we have been using these formulas for more than 80 years now, but we also know that these are not true, because today we have the power of CFD modeling, and we can check the radiant section, the burners, we can check the flue gas temperature profiles, we can check the flame length, we can check heat transfer to the tubes and location of hotspots. So what I feel is it is important to do CFD modeling and make sure that, hey, when we designed the heater, we assumed uniform heat transfer in radiant section. Is it true? Are we getting uniform heat transfer? If not, we need to make necessary adjustments in our design to mitigate some of these factors, And you can do that because we have CFD available, and we can ensure that by CFD, we take care of most of these parameters. We also did a survey on the burners. Typical coker heater had about 64 burners. The range was from 3 to 144. Design heat release per burner was about 3 million BTU average. Burner to tube spacing about 4 feet or even less than 4 feet, 3.7. The lowest was 2.5 and 6.8, And then comes the burner to burner spacing for uniform heat transfer. We found it was 5 feet burner to burner spacing. That was an average 4.7 feet. So I just want to show you the effect of different parameters and how they play a part in your fired heater run length. So this is a plan view of a double fired coker heater. And if you look at overall on the picture, everything looks all right. The burners are there. There are 3 rows of burners. The center burners are, I think, almost every 4 feet. There are 2 rows of burners on either side, and there is 2 rows of tubes. But this coker heater is having a lot of issues. This heater is having a run length of only about 3 to 4 months. So some of these parameters may be more important. And one of the parameter which I find is important is the burner to tube clearance. And the reason I say is the ultra low NOx burners have very long flame lengths. And when they have long flame lengths, the flames can lean actually. Flame is nothing but gas jet, and it can always lean. These burners flames get affected even by wind velocities. So some of these things could make a great impact. And flames are very, very high temperature gas jets. Typical flame temperature could be anywhere between 2500 to 3000 degrees, So you can see how the burner layout or the heater layout can affect the run length and other parameters, I want to tell you a little bit about the tube metal temperature calculations. We do tube metal temperature calculations at the start of run and at the end of run. This is for one heater, which is a single fired heater. And it was 4.25 inch OD, almost 0.6 inch wall. We assumed quarter-inch coke. And we calculated the mass velocity, we calculated the heat transfer coefficient, and then we calculated the maximum flux and the maximum tube metal temperature, assuming a fluid temperature of 950, starts with about 1082 at the start of run with no fouling and almost 1255. Maybe that is the limit of even the coil metallurgy actually. So that's basically the start of run and end of run, Now, if you look at this example and say, hey, I will have 1 degree temperature increase per day, how will that affect? So we plotted this, and if you use 1 degree temperature rise in tube metal temperature per day, 1 degree Fahrenheit, it will take you 87 days to reach EOR or maximum TMT of 1255. So you can see it is not good enough. You don't want 3 months run length of your heater. We are looking at lower temperature rise. If you want 1 year run length, then typically say about half a degree is what you would like to get control, That's how you should control your run length, about half a degree. And that is valid for P9 material where the limiting design temperature is 1300. Please make sure your tubes are designed for 1300 because it requires higher thickness. The other option is, and a lot of refiners have opted for this change, is to upgrade the metallurgy to stainless steel 347. And that gives us about 1500 degrees temperature limit. And there, if you see, we can afford to have a 1 degree temperature rise per day, So I want to show you the coker heater tube skin temperature profile. This is from that same heater where I showed you the burners and tube layout, the plan view. And if you see over here, It's almost 3 months. Within 3 months, it was reaching the design limit of 1200. Here, I think it did little better, maybe about 5 months, but here it did it about 3 months again, and here it did even less than 3 months. So if you see the temperature rise, they had to clean almost every uh, 3 months, 3 or 4 months, which is not acceptable. That requires a lot of effort. You shut down your coker heater for 5 to 7 days. You hire a pigging company to clean it, or you do steam air decoking. So a lot of problems. So the best thing is to minimize coking. So I want to present to you two studies, and this is a double fired coker heater, and the client was experiencing high tube metal temperatures in the lower tubes. So this is, as you can see, this is 4 cells, a very big coker heater with 8 passes and 4 convection sections and one very large tall stack. That is the configuration. So if you look at the configuration in detail, it was 4 burners. If you see over here, 4 rows of burners, 2 rows of tubes, a central bridge wall in the center. So that was the construction. This heater had 4-inch tubes in the top, 30 tubes, and bottom tubes were 5-inch NPS schedule 160. And this was having a lot of problems actually. And then the client told us they were having maximum coking in these lower 5 tubes. That was, and they were still having high tube metal temperatures somewhere around 2/3 of the height of the box. But these were also coking up very fast actually. So we studied it, and we came up with several different revamp options. We said, okay, let us take your four radiant tubes which are at the outlet and change them with 6 4-inch NPS schedule 120 tubes. Now, client wanted to upgrade the radiant and convection coil metallurgy to 347H. So we gave him a lot more options. We told him, hey, if you are retubing it, we would like to see some modifications. And we gave them a modification in option 1 of putting 2 extra tubes on the arch, per pass. In the second option, we gave him 6 tubes at the arch. And in the third option, they had 2 rows of provision of 2 future rows in the convection section. And we said, hey, let's do this as well as add 2 more rows in the convection section. So basically, we gave him 3 upgrade options. And when you give them these options, you see the effect is very, very different, a profound effect. From 11,000 flux, we went all the way to 8,000 flux, 25% reduction in flux. We reduced the tube metal temperature from 1100 to 1057. And we also reduced the firing from whatever they were firing by about 8%, which is very, very profound. So keep an open mind whenever you are retubing your coker heaters and look at different options. Look at it is not necessary that whatever the heater vendor gave you 20 years ago, that is the optimum configuration. You can always upgrade, just like a computer. You can always upgrade the memory, you can always upgrade the hard drive. Similarly, you can always upgrade the metallurgy, you can always upgrade the number of tubes, you can always add more tubes. And those incremental costs are very, very low, especially when you're spending millions of dollars in retubing. We had the similar recommendation on their existing burner layout. They had 14 burners per row, total of 56 burners in each cell. And these were ultra low NOx fuel gas fired burners. And we said, okay, let us do the CFD modeling and see what we find out. We did the CFD modeling of these burners, and we found out that the flames were almost touching the tubes. I mean, if you look at D1, D2, D3, they are less than a foot. In fact, 6 inches. And this is at ideal conditions. And if you have wind blowing, if you have anything else going on, higher excess O2 or lower excess O2, the flames could. And that's where they were having hotspots. So we came up with the conclusion that these burners are not meeting the required heat distribution profile or the uniform heat distribution profile. So without asking them to spend too much money, we said, okay, let's take your existing burners and put them at about 7-degree angle. So we took the existing burners and then moved them outwards by about 7 degree. And when we do that, we are able to increase the minimum distance from the flame to the tubes to more than 2 feet. So, and typically 2 feet is the minimum accepted distance in the industry. So that's basically what we did, and it makes a lot of difference. I want to show you the second case of, again, coker heater retubing. This one is a single fired coker heater and a conventional coker heater with twin cells. There were 2 such heaters, so basically 4 cells again, and each cell was having 2 passes, common convection section, very central bridge wall with burners inclined at 15 degree. Again, this company was facing a lot of problems. They were decoking every 6-7 months. The tube life was very low, almost about 5 years. They were getting longer flames, and also they were having firing imbalance, which is the outside burners were required to be fired 30% harder than the inside burners. So that was another firing imbalance which was taking place, which is kind of unique to this heater. I've not seen it in other heaters. So again, we did the CFD modeling, and as you can see, even though the burners are 2 or 3 million BTUs, the flames were almost like 12 to 13 feet. That's how the flames were there, and we were getting high. You can see over here the high tube metal temperatures in the roof tube. That's where they had the most problems, somewhere over here. So the client said, hey, I want to go for retubing. And we said again, okay, if you're going for retubing, let us do something else. Let us give you some upgrade options. So we said we can put more tubes, we can put higher diameter tubes. And the client went with our recommendation. We ended up putting larger diameter 66 tubes. And this is the before and after, scenario. We moved the tubes up by about 2 feet and also installed a baffle to make sure they are protected from high flue gases. And when we did that, the performance of the heater improved substantially. This project was done about 3 years now. And you can see over here, we were able to reduce the flux. We were able to reduce the firing bridge wall temperature, and even the fluid mass velocity we were able to improve. I would want to tell you about do not overlook your convection sections. Convection sections are very important, even though we focus most of the time our attentions on radiant sections, but convection sections can help you a lot because it's easier to change them. It's very inexpensive because they are shop fabricated. We take out old one and put a new one, and we can redesign the convection to maximize the process heat recovery. In this one, you can see we had 4 tubes per row. We redesigned it with the same width to 6 tubes per row using smaller tubes, and we were able to reduce the flue gas approach from almost like 200 degrees to about 40 degrees. So that kind of gives us another 5% improvement in the firing rate or in the efficiency, So any reduction in the firing rate counts a lot, So, so much for the revamping or case studies. I know all of you have coker heaters in your units. These are some tips over here: increasing excess air to the burners and increasing boiler feed water steam injection to the coils to maximize coker heater pressure drop available, especially if you're running your heaters on lower charge rate. So steam injection will definitely help you. This is a coking rate profiles with no coking to this is there's no coking, which has never happened. So this is typically about 1% case over here. And if you go to 3%, you do reduce some coking. So depending on the pressure drop available with you, you can go for maximizing the steam injection. It helps. It will help you, depending on how much pressure drop you have, it will help you. This is the tips for revamping. Always make sure you don't retube it in kind. As I said, always upgrade. Always look at the convection section. Always try to look at the burners, do CFD, uh, install them at an angle to direct the flames away from the tubes. So when we were doing the database, we developed a coker heater coking index, and we took these 7 parameters. 3 are the average radiant heat flux, mass velocity, coil diameter, which figure in any heater design from the coil side. But we added 4 more parameters over here: burner heat release, burner to tube distance, burner air side pressure drop, and burner to burner spacing. And our focus is try to achieve lowest possible coking index. I want to show you a quick comparison of 2 heaters, coker heater 1 and coker heater 2, where we kind of did a comparison. This is from 2 jobs which we worked on. And if you look at it, coker heater 1 was designed for lower heat flux, higher mass velocity, but has a higher coking index. The other heater is designed for higher heat flux, lower mass velocity, but has a lower coking index. So just keep your options open, You have to make sure that you look at the complete picture, not just look at the computer output. Look at the heater configuration, look at your burners, look at the flames, and try to make sure your heater has a low coking index. If you want any help, you can always send your coker heater details to us, and we will calculate the coking index and give it back to you. And we can also tell you where you stand with respect to all other heaters, what is the range. If you're thinking of installing a new heater, these are some guidelines from my side. Use lowest heat flux, use highest pressure drop, highest mass velocity, highest number of burners, carry out CFD modeling, carry out burner performance test. And last but not the least is higher furnace improvements. And I assure you, you will get the best coker heater for your money. We will use our experience to work with the heater vendor, whomsoever you select, to get you the best coker heater that you will be happy for the next 25 years. Challenge us with your projects. So thank you very much. I thank you again for spending time with me and giving me a patient hearing. I appreciate your time, and I will now open the presentation webinar for the for the questions and answers. If you want to send me any questions, I do see some questions here. So I have a first question from, can you please explain the usage of various boiler feed water injection points in coker heaters? Generally, we inject boiler feed water at convection inlet along with the feed, but when to use alternate injection points like at crossover or near the radiation? Very good question. The inject depends on how much pressure drop you have. If you inject it at the convection inlet, you will have two-phase flow throughout the coker heater and it will increase the pressure drop. If you inject it at the radiant inlet or the crossover, you will have lower pressure drop, and maybe you can inject more boiler feed water actually. So there is going to be some benefit. I mean, so generally most vendors will give you 2 or 3 injection points. What is the maximum allowable heat flux during revamp scenarios if there is some margin in another design parameter? So Ganesh, I think, as I said, the maximum allowable heat flux could be around 15,000 for coker heaters, double fired coker heaters. You can even go higher actually, but you have to ensure that you don't affect the coking, you know. So make sure if you have margin on burners, if you put more burners, as I showed you the comparison, you will be better off. Which is better, pigging or steam air decoking? So they're both equally good. It depends. However, in US, most of the people are going for pigging these days because pigging has advanced and pigging has improved. So you can go for pigging, but you can also do steam air decoking. When steam air decoking is done in-house, so there is no expenditure. You don't have to pay another company, outside company, for doing pigging. So, but in US, more people are going for pigging. It is faster, it is cleaner, so that is some of the advantages of pigging. But you can always do boiler feed, steam air decoking also. Boiler feed water or steam injection, most of the people do boiler feed water injection. Some people do steam injection, but most of the people, yeah. Coker index, the lower the better, yes. That is right. You have lower heater, which is, it will be coker. Whether any chemical is there in use to add along with the feed to increase the coker run length, I don't recommend any chemical injection. I think you should do the root cause analysis and try to maximize the coker run length without any chemicals. Chemicals are very expensive, and we had an experience where client was injecting chemicals. This was in the crude heater, not in the coker heater, but he was spending millions of dollars, and we fixed his heater and no more chemical injections. What is the best location to measure the outlet temperature? I think third tube from bottom is fine. Even the outlet is fine. I don't see a big difference by that time. I think the temperatures are, yeah. What is the general run length nowadays with upgraded heater technology? I think you want to get at least 12 months out of the heater. That would be a general, But most of the heaters, as I said, are 3 to 6 months. Typical, that's what we are finding most of the heaters. How to get reliable TMT measurements in the event of faulty tube skin thermocouples? Again, very good question. I want to tell you that there has been uh, a lot of improvements or developments in the TMT thermocouple technology. The two metal temperature indicators are very accurate now and reliable. At the same time, the infrared monitoring has also improved a lot, actually. In fact, you can even do it using your iPhone. There is an app and there is an attachment you can use to measure the TMT. So there is a lot of, what I suggest is cross check. You know, in US, typically a lot of these companies are doing it every 3 months, infrared surveys, and that gives them a good comparison tool. Will the steam injected change the characteristic of the feed? Yes, it does. It does not change the characteristic. It improves the vaporization. We have typical issues of furnace pigging since commissioning of at IOCL Gujarat. Can we post our query to you directly? Absolutely welcome. We will be more than handled to work with you. If we have separate radiant and separate convection sections and common stack, does it hold to increase our run length? No, it does not actually. Basically, again, the coking has to be there in checked whether it is happening in radiant section or in convection section. Is there any coating which increases the run length? What there are coatings available, but I don't recommend them. Basically, the coating claims that your emissivity will increase from 0.9 to 1, which is very, very marginal. And when you do coatings, you are not taking the root cause. You are not taking out the root cause of the coker heater. So you have to ensure that you eliminate the root cause, which is scaling in coker heaters. Is symmetry affected the run length? It does sometimes. I don't have a direct experience of coker heaters, but I do have experience in crude heaters where the inlet piping symmetry or the manifold, yeah, does affect the run length. Will more boiler feed injection hurt run length or for additional duty requirement to vaporize this thing? Very good question. I think I did not cover it, but the more boiler feed water you inject, the higher will be the duty. In fact, if you put 3% boiler feed water as compared to no boiler feed water, the duty will go up by 15%. So there is a point where is a point of diminishing returns. Our recommendation will be to do it when the heater is mostly at turn down. That's where I think you will get it. On single fired 4-cell, why do outside walls cell fire harder? We see this effect and inlet convection outlets are hotter. Yes, I think when we did the CFD, we verified that this is happening, and that is because the convection section in the center and the flue gases tend to bypass. So the heat transfer is not taking place in the outside cells, and that's what is kind of happening. What happens? What frequency of spalling in heater pass? I would say every 2 to 3 months. That's typically how they do it. Is feed property determines run length? Yes, feed property does determine run length. My thinking is coker heater is like a mother of all heaters. all the refinery residue, whether it is from atmospheric, vacuum, hydrocracker, FCC, everything is coming finally into the coker unit, So that's where you typically don't control what is going to the coker. So question is, can we coat internally to avoid scaling? Yes, you can do that. In fact, 30, 40, 50, I would say 40 years ago, they used to coat these tubes with aluminum, and the process was known as alunizing. They would do aluminum because aluminum repels carbon, but what they find is it is a lot more expensive actually, but we could do that too. So I got how does feed properties affect run length? My coker heater is 20 to 30 days run length, which is horrible. Feed S14 is very, very high. I think, Mel, let us talk separately, and I would be definitely be happy to look at your coker heater and see if we can help you out. Is it advisable to go for spalling, looking at run length greater than 6 months, even though TMT are low? Or can we wait for TMT to go? I would suggest there are two issues here. Now, there are two factors, tube metal temperature and pressure drop. Most of the time, TMT limit is hit the first. So if your TMT is hitting first, you will be decoking it, but you also check the pressure drop. And you can do a spalling every 6 months. I think it will be good actually, and then you can extend the run length. All right, I think how critical is sodium content in feed for heater run length? I think sodium does promote coking, but I'm not a process expert. I'll be very honest with you. I'm a heater engineer. So that's typically. So again, thanks a lot uh, for attending the webinar today. I thought it was a good interaction with the number of questions what we got. And hopefully we will talk again. And please, if you have any coker heater issues, we would like to help you out. Send us your coker heater details and we can look it over and help you. Thank you all.